Great, thank you so much for the introduction, and there should be plenty of time for questions at the end, and I'll also stick around afterwards. Hopefully won't keep you too long for lunch. To set the stage for this talk, errors in ML models can lead to downstream consequences. So for example, errors in ML models have already led to fatal accidents in autonomous vehicles. And this is just a general trend where errors in these ML models can have these extreme consequences. They're used in things range from recidivism protection to, as I mentioned, autonomous vehicles. And this is particularly problematic because there's no standard way of doing monitoring or quality assurance over these ML models, despite being placed in these high-stakes scenarios. However, if we take a step back and look at what I call software 1.0, or software without ML, this is also deployed in mission-critical settings, ranging from medical devices to rockets. And if we look at the software 1.0, pretty much every piece of important software is monitored and has rigorous quality assurance. So we have a whole suite of tools ranging from assertions to unit tests to regression tests, fuzzing, et cetera, for software 1.0 that isn't really available for software 2.0. And so in my research, I asked the question, can we design monitoring and quality assurance methods that work across the ML deployment stack? And in this talk, I'll describe abstractions for finding errors in ML deployments and in labeling pipelines. What we'll use to find these errors is that these errors in models and labels can be systematic. So for example, what I'm showing here is a single-shot object detector over a video from a street corner. And we can easily specify, without knowing anything about this model, that cars shouldn't flicker in and out of this video in this unrealistic way. And similarly, if you look at labeling pipelines, the actual data labels used to train these models, we can point out that the labelers consistently miss certain kinds of objects. For example, these motorcycles, which are relatively small in the video. And you might ask, well, these errors seem kind of trivial. Why do I care about them? Well, if you look at the safety report for the Uber self-driving fatal crash, it reads, as the automated driving system changed the classification of the pedestrian several times, alternating between vehicle, bicycle, and another, the system was unable to correctly predict the path of the detected object. And so as we can see here, even these seemingly simple errors can lead to cascading consequences when placed in these larger systems. So it's critical to catch these. In this talk, I'll describe two abstractions we developed to find errors in these ML models and these labeling pipelines. The first are model assertions, and the second are learned observation assertions. And I'll go through each of these in turn, starting with model assertions. And I first want to put model assertions in context. If we look at a standard ML deployment pipeline, it has things ranging from data collection and labeling to model deployment and training, to statistical validation, and development and monitoring. And there's been a lot of work in the literature on some parts of this stack, in particular the statistical validation and the development and training parts. But there hasn't really been much on the first and last parts here, which model assertions focuses on, and it can also be used for the other parts as well. And one interesting thing about model assertions, as I'll describe later, is that many users, potentially not even the model builders, can collaboratively add assertions. And so as I mentioned with the example from the video, even someone who knows nothing about how the model was created can still help find these errors. So first, what are model assertions? Model assertions are opaque functions that the user provides. The inputs are a history of inputs to the ML model and the predictions from the ML model itself. So concretely, if you go back to the video use case, the inputs to the model assertion are the inputs to the ML model, for example, the frames, the pixel buffers of the frames, and the outputs, the bounding boxes. A model assertions output a severity score, which is a floating point number, where a 0 is an abstention. These model assertions can often be specified fairly easily. So as a concrete example, we can specify that predictions from different autonomous vehicle sensors should agree. So what I'm showing here are two predictions from different sensors, a LiDAR sensor and the camera. And as we can see, the LiDAR predicts a truck and the camera predicts a car. And so we can specify that necessarily one of these predictions is incorrect. And for this exact assertion, I specify the pseudocode here, which there's just one function here, which is no overlap, which is basically checks to ensure that there's no overlap between a specific box and the LiDAR versus the cameras, but as we can see here, it's relatively easy to specify these with relatively few lines of code. In addition to allowing users to specify model assertions in a completely black box way, we also have what we call the Consistency API. And the Consistency API allows users to specify two kinds of assertions relatively easily. And the first is that transitions should not happen too quickly. Specifically, if we look at this here, here we're trying to say predict people in a video. The first person appears in timestamps 1, 2, and 4, but not in timestamp 3. And this is very likely to be an error. The Consistency API allows users to specify this. Similarly, within the same scene, the person 1 has predicted attributes of male and female gender, and also brown and black as the hair color. So assuming some temporal consistency, one of these is likely to be incorrect. As an example, we deployed the Consistency API for TV news analytics. And the consistency assertions basically say that overlapping boxes in the same scene should agree on the attributes. And as we can see here, I apologize for the font. On the left-hand side, the person is predicted to be Christy Paul, and on the right, Poppy Harlow. And as we can see here, one of them is wrong in this scene. Now, perhaps surprisingly, in addition to specifying when errors might be occurring, model assertions can also be used to improve ML models. And one way to do this is as follows. Given a set of inputs that trigger an assertions, we can pass these inputs to excuse me. We can pass these inputs to human labelers to generate labels, and then retrain the model. One thing I want to point out is that this is agnostic to the data type, task, and model. And you can view this as a new data collection API, which is in contrast to a lot of standard methods, for example, active learning, which require some domain knowledge about the task. Now, this raises a natural question, which is how should we select data points to label for active learning? And to understand why this is an issue, let's say that we have two assertions, and the first assertion flags these two data points, and the second assertion flags these two data points. As we can see, many assertions can flag the same data point, and the same assertion can flag many data points. So given a limited budget of labeling, which point should we label? I won't have time to talk about it in this talk, but in the paper, we developed a model assertion-based bandit algorithm, which is essentially an epsilon greedy bandit algorithm, for those of you familiar with this line of work. To evaluate model assertions, we deployed model assertions on real-world datasets, including a video analytics dataset, a self-driving car dataset, and an ECG reading dataset. And there's more examples in the paper. If you remember, we had two goals. We want to find errors and retrain models. And so to measure this, we measure the precision of finding errors. So this is basically saying, if the model assertion triggered, is there actually an error in the data? And for the model retraining, we use the metric of mean average precision for the video analytics use case, which is a standard metric for accuracy for object detection. The first thing we show is that model assertions can find errors with high true positive rate. So as we can see here, across these three settings and 5 assertions, the true positive rate, in other words, if we actually, when the model assertion triggered, is there actually an error, is at least 88% across these 5 assertions. And in addition, these assertions can be specified with few lines of code, as little as 11 and at most 23 in these 5 examples. There's other examples in the paper. So for example, we can even apply these on natural language datasets and also tabular datasets, which might be of interest to this audience. And if you're curious about this, I'm happy to chat about this offline. We also evaluated model assertions on the metric of mean average precision for retraining. And we compared this to random sampling in the data and uncertainty sampling, which are 2 standard ways of retraining models. As we can see, using model assertions to retrain models substantially improves the performance. And so, for example, if you want to achieve a mean average precision of 62%, you can almost half your labeling budget. To give a qualitative sense of what this looks like, what I'm showing on the left is the original SSD on this dataset, and on the right, the best retrained SSD. And here, this is on the same scene of data. As we can see, the best retrained SSD is substantially more consistent than the left-hand side, the original SSD. So now that I've described how to use model assertions to find errors in ML models, I'll now describe learned observation assertions, which primarily focuses on finding errors in the human labels used to train these models. And if we look at how models are being trained today, the data that's used to train these models is exploding. And so, for example, labeling vendors like Scale AI have millions in revenues and hundreds of customers, ranging from places like OpenAI to autonomous vehicle companies and others. And what's perhaps surprising about this data is that this training data can be rife with errors. What I'm showing here is a real-world autonomous vehicle data set where the boxes in red were missed by the human labeler. And I just want to point out that this data is being used to train models that are being put in cars today. So if you ever decide to get in one of these. And so as we can see here, even the best-in-class labeling services miss critical labels. You probably don't want to miss that car if you're driving. And so going back to our pipeline from before, where we have the standard pipeline for deploying ML models, this component here, this data collection and labeling, is really critical for high accuracy models. But there hasn't been much work done to vet the data used to train these models themselves. So how can we go about doing this? Well, one way we can do this is to use model assertions. And the way this would work is as follows. Let's say we have human annotations here in orange. And we have a model prediction in blue here, which is this truck, which was missed by the human labeler. Well, by taking the difference between the model and the human, the model predictions and the human annotations, we can surface likely errors. And this is great in some circumstances, but unfortunately, models can be unreliable, as I, in fact, showed in the first part of this talk. And so, for example, a model might predict that this street lamp as a car. And so you're going to have a lot of false positives if you attempt this approach. And to address this, we developed learned observation assertions, or LOA. And going back to our pipeline from before, LOA primarily focuses on the left-hand side here, the data collection and labeling, but can also be used for deployment and monitoring. And I also want to point out that this is critical for safety and liability reasons, especially for high-stakes scenarios, for example, autonomous vehicles. So instead of having users manually specify when errors might be occurring, LOA works slightly differently. The application user will specify features over observations. For example, this volume feature, like I'm showing here, which shows which computes the box volume of a 3D LiDAR box. Then, under the hood, LOA will learn typical distributions of these features. And then one other thing that the user specifies are associations between different observations. So the workflow is as follows. The application user specifies these boxes in blue here, the features and the associations. And the system administrator will specify historical data for LOA to learn distributions, and also the new data to find errors in. And then LOA will output the errors ranked by likelihood of actually being an error. So to find errors, LOA requires two what we call organizational resources, which are resources already present in ML deployments. And the first are ML models themselves. As we mentioned, ML models can provide information about potentially missing tracks, and so we use this to surface likely errors. But also, as we mentioned, models can be unreliable, and so we want to filter out these false positives. And to do this, we use a second form of organizational resources, which are these existing human labels. And these existing labels can provide examples of expected behavior. For example, the box volume that I specified earlier, and also things like track lengths and object velocity and other features as well. Given these organizational resources specified by the system administrator, LOA will learn feature distributions, which tells us which feature values are likely to be likely or not. And as a concrete example, if a car is going at 300 miles per hour, it's probably not, there's probably an error somewhere. Then under the hood, LOA will construct graphical models from these features and these associations and use this graphical model to score which ones are likely errors. And the full details of the scoring mechanism is in the paper. Then, using these differences between labels and model predictions, LOA can surface the ones which are likely to be errors. Just to give you a brief overview of how the scoring works, we sum up some of the feature distributions and we apply some application-specific transformation. I won't have time to get into this for this talk, but as I mentioned, all the details are in the paper, and I'm happy to chat about this offline as well. To evaluate LOA, we deployed it on 2 autonomous vehicle datasets. The Lyft Level 5 dataset, which is publicly available, you can download it now. If you want to be horrified, you can look at some of the labels that they produced. And we also deployed it on the Taylor Research Institute internally, which is an internal dataset generated by a leading labeling vendor for training autonomous vehicle models for deployment. And if you remember, we had 2 goals for LOA. We want to find errors, and we also want to find them without spurious predictions. And so to measure this, we use 2 metrics, recall for finding errors, and precision for finding them without spurious predictions. The first thing we show is that LOA identifies errors in human labels in these real-world datasets, starting with the Lyft Level 5 dataset. We deployed LOA per scene, and here a scene is a 5 to 15-second clip. And after deploying LOA, we found errors in 70% of the Lyft Level 5 dataset validation scenes. And this is particularly problematic because this dataset is being used to train models, host competitions, and has been cited hundreds of times. And we want to ideally not have these kinds of errors. We also deployed LOA internally at the Taylor Research Institute. And here, the labeling vendor that was used has an SLA for accuracy. And so despite this SLA, we can see that there are a number of errors present in the labels, including the missing motorcycle on the top here and this missing car, both of which are within 20 meters of the autonomous vehicle, which is somewhat problematic. In order to measure the recall, we took one scene, which had a large number of errors, and we manually annotated the scene exhaustively using an expert labeler, yours truly. And we found that deploying LOA was able to find 75% of these errors in this exhaustively examined scene, showing that it can achieve high recall. And so high recall is great, but if you're going through tons and tons of false positives, it's not super useful. So we also deployed LOA to see if we could find errors with high precision. And so Fixie here is a system that implements LOA. As we can see, deploying LOA can boost the precision for finding errors in these data sets, sometimes by up to 2 times. We also deployed LOA to find model errors without human labels. I didn't describe how we did this, but it's a very similar process. And we deployed LOA across the same 2 data sets that I mentioned before, the Lyft Level 5 dataset and the Taylor Research internal dataset. And we deployed state-of-the-art LiDAR detection models. We also excluded errors found by ad hoc model assertions. So the results on the next slide that you'll see, we took all errors found by expert developers looking for errors manually and only looked for new errors. And so compared to uncertainty sampling, which is a standard way of finding errors, LOA can almost find errors with 2 times higher true positive rate or precision. And once again, this is excluding the errors found by model assertions. And as an example of a model error, what I'm showing here in orange are ground truth correct human labels, and in black the prediction from the ML model. As we can see, this prediction with a black box is inconsistent over time, but it does overlap. So it won't be found by an ad hoc model assertion using this kind of flickering assertion, but it will be found by LOA by specifying when these feature distributions are unlikely. For example, the box volume is not consistent over time. Everything that I talked about in this talk is publicly available, including the papers and the code used to generate these results. If you are also interested in using this for NLP or tabular data, the OMG repository has has examples of this, and I'm happy to talk about this offline as well. But in conclusion, errors are rife in both training data and in the ML models at deployment time. And in this work, I described two abstractions, model assertions and LOA, which can be used to find these errors in both the data itself and also the ML models at deployment time. And I think as a community, we need more work on the ML deployment stack beyond just training. And thank you, everyone, for coming to my talk. My email is here if you'd like to contact me offline, and my Twitter is here as well if you'd like to give me a follow. But we have plenty of time for questions, and also plenty of time to get to the lunch line early. So thank you so much for coming.
Any questions for our speaker?
Great talk. I'm looking forward to reading the paper. And this is probably in the paper, but do you do anything to scale the feature distributions for depth of field? So say, some of the smaller cars are actually just further away, and a valid new car could be, significantly bigger because it's closer?
Yeah, so we don't do anything for that because we specifically deal with LiDAR data in the experiments that we looked at. And LiDAR data has 3D information. So the field of view doesn't matter for that kind of data. Now, if you want to deploy this specifically over vision data for these autonomous vehicles, you probably have to do something like that. But we didn't explore that in our paper.
Very cool talk. It's exciting to see all the errors you found in the Lyft data set. I'm curious, when did you try reporting these to the original creators of the data set and see what the response was? Are these expected? Are these something they can fix in their future workflows?
Yeah, that's a great question. We actually reached out to the creators of the Lyft Level 5 dataset with no response. There was one response, which is that they claimed that there were some labeling guidelines that they didn't release, and so we asked them for these guidelines, and they didn't respond with that. So it's unclear to us what the expected result should be. But I think what's particularly problematic is that if you look at how these datasets are being used, there's a ton of LiDAR models which are being developed on these datasets, and as far as I can tell, none of them know about these so-called labeling guidelines. And they're being used to evaluate whether models are good or not on this erroneous data. So we think it's particularly problematic, even if there are some things that could be fixed about the data itself.
Thanks.
Okay, let's give it up one more time for our speaker.